Okay, the solutions to exam 4 here. Number 1, we had a random variable with a given PDF, except that we had a c here, a constant that we weren't sure what it was. So that was part A. We do know that if we integrate across the entire PDF, we're going to get area equal to 1 if it's a valid PDF, which we can assume here. The only place where x is non-zero is between, where the f of x is non-zero is when x is between -1 and 0. So we put those as the limits of integration over the function. Go through, integrate, and we get 2c plus 1/2. Remembering that that all equals 1, we solve to get c equals 1/4. We can check that, so we put that 1/4 back into the original PDF, get 1/2 minus x, which we can graph. That's a line with intercept at 1/2, slope of -1, so we can graph that pretty quickly. It's a quadrilateral, it's actually a trapezoid. You could do it a couple different ways, either do the triangle area and the rectangle area, or you could simply realize that the trapezoid is the center, the average of the two bases, which in this case is 1 times the height, which is also 1 times 1. So that does work out to an area of 1. What the CDF is, so this is just the general definition of a continuous CDF. Up until we get to the point where x, well, I guess we have it down here, where x is -1, the CDF is 0, so there's no probability there. Here's the part that really we have to do a little work for. So this is the PDF, this is f of x. We want capital F of x, so we want the integral of this. Now we can't just take the integral across the domain. We want to go from -1 up to any given point x, because we want our CDF as a function of x. If we would just put this at 0, of course we're just going to get out 1, because if we integrate across the entire PDF, we're just going to get 1. And we don't want to do that. What we want to do is to be able to choose any x within here and figure out how much of the area we've covered so far. To do that, we have to integrate from -1 to an arbitrary x. This function, I'm just using t and dt here to not get it confused with this x. And we integrate that. It gets a little bit messy here because we have this -1 at this point. Keep in mind that this is the higher value, so we start by evaluating that, and then this. Notice also that I'm pulling out a 1/2 from everything, just and then putting it back in right at the end. You could, of course, evaluate this thing at x minus, and put -1 in here for t also. In other words, you could leave the 1/2 in there. So that works out to give us x over 2 minus x squared over 2 plus, and notice here I originally got 2 because I forgot to distribute this 1/2 to my final 2 there. But that was picked up in my check. In my check, I looked at the geometry. I just took an arbitrary point. Now this isn't necessarily going to catch every error, but it can certainly catch if there's something that's off in general, it'll catch it. So I know that capital F of -1/2, in other words, how much of the area have I covered so far by the time I'm at -1/2. So I calculate this area geometrically using the same trapezoid idea as in the part A, and that gives me 5/4 times 1/2, or 5/8. When I substituted in -1/2 into this capital F of x that I had found, I did not get 5/2, which was a trigger. In fact, I was off by 1, and that's what clued me into, hey, I forgot to distribute my 1/2 out here. Once I put 1 there, then this was also 5/8, and that check was complete, and I was satisfied that this is the correct capital F of x. And then, of course, if x is anything greater than 0, by that point, we've covered the entire possibilities, the random variable, the values that it could have. So from that point on, it's 1. let x be a continuous uniform random variable. So we're on the interval 0a. If the expected value, if the mean is 5, and it's going to be this continuous line, think of 5 as the balance point. If it starts at 0, 5's the balance point, it has to go through till 10. Now you could do that more rigorously, that would be fine. Integrate this function from 0 to a. Maybe you could integrate x times the function, which you could put as c, from 0 to a, and let that equal to 5. Also integrate under there, let it equal 1. Or you could just see that 5 is the balance point and that that's going to end up as 10. However you do that would be fine. And the second part, the PDF, so again we have this definition of, well, here we're actually setting the integral under this this line right here, this line segment right here, equal to 1. And since we know it's a width of 10 and the area is 1, the height has to be 1/10, and it's a constant 1/10. So this, between 0 and 10, we're just at y equals 1/10, or f of x equals 1/10. Everywhere else it's 0. Okay, we have an exponential distribution here. First one's pretty straightforward. Notice we have our PDF and our CDF here for this given one because we have lambda of 1/2. Between 2 and 4 hours is just going to be capital F of 4 minus capital F of 2. So this is all the area under the curve from 4 to the left. Then we subtract out everything from to the left of 2, and that leaves us just with the area between 2 and 4. We could also integrate this PDF from 2 to 4. That would be perfectly fine. Either way, we should get about 0.23. Now here we have a conditional probability that it takes less than 4, given that it takes greater than 2. So you might think at first this is the same problem as A, but it's not, because A, we could still die in those first two, or sorry, I'm thinking of a different type of problem. So we could still have it repaired between 0 and 2 hours. It's possible it would take less than 2 hours. In part B, we know that it's not taking less than 2 hours. So that part of the distribution is already removed. So we're only looking from 2 onwards. And we also know by memorylessness that from 2 to 4 is the same as from 0 to 2. So the probability we're less than 4, given that we're at 2, is the same as starting off, we're within the first 2, which is just capital F of 2. And we can just plug that 2 then into this CDF. Okay, we have normal distribution here. We want the probability that the rainfall in terms of x will be less than 42. So subtract the mean and standard deviation from both the left and right sides of this inequality. The left, of course, is another way of expressing the standard normal z. This here boils down to 1/3, and 62.93% of the normal distribution is to the left of 1/3. We can get that from the table, which should be on the last page of your test. Now here we have a little discrete thing that should take us back to the previous chapter 4. So we want in exactly one of the next 4 years less than 42. In other words, the other 3 out of the 4 will be greater than 42. Keep in mind that the probability of getting exactly 42 is 0 when we're measuring on a continuous scale. Even if it's reported as 42, it really was something else. So we have 4 choose 1, because we have to choose which one of the 4 years will be the less than 42 year. Then for that particular year, as we found in part A, 0.6293, we have one of those. In other words, there's a 37% chance of having more than 42, or greater than or equal to, since technically we didn't say the equal here. So that would be 3 of those years. So when we multiply all this out, we get about a 12.8%, which sounds reasonable, certainly, because we know if it would be a 50-50 chance, it would be 1/16, and we do have a little better chance of that, of getting rainfall in a year. Okay, and by the way, 50-50 chance would not be 50-50 chance, we would still have to do 4 choose 1 and then 0.5 to the fourth. Sorry, I shouldn't have said that so rashly. So that would actually be a 25% chance. And because we have to have more of these non-rainies, which is more difficult, we have lower than 25%. My apologies there. Okay, on number 5, we have this game where there's 2 possibilities. We roll a 6-sided dice. If we're between 1 and 5, we just get that many dollars. If we get a 6, then there's some kind of, maybe they type it into a exponential random exponential distribution and get out our result there. We know that the mean is 5. Exponential distribution, though, we could theoretically get 100, 200, 1,000. All those are possible values because the exponential distribution starts at 0 and goes towards infinity. So, and we also have this information that it does cost $4 to play the game. The reason I put this note in here, and one of the problems, it was assumed that if your expected profit was less than 0, you wouldn't even play the game. That's why I wanted to make sure I clarified that there. So their expected profit is really in 2 parts. It depends, first of all, if we get 1 through 5, that's controlled by this probability, and then how much we would expect to get in terms of that. Or we could have the probability of getting a 6 and the expected profit we would get in that. There's different ways to do these variables. We could have done it as a conditional on P, but either way is fine as long as you have it separated out in your head. And then we have -4 because we are paying $4 to do the game. So we have $3 is our expected value on a uniform distribution. We can get that 1 plus 5 divided by 2 would give us 3. 5/6 chance because we get 1, 2, 3, 4, and 5 out of the 6 options. Over here, notice we really don't have to mess with the exponential distribution at all. All we need is the expected value of it, which is 5. So we have that 5 times the probability of getting that exponential, which is 1/6, because we have to roll a 6. Add all that together, and you have a loss of about 67 cents per game, which makes it a reasonable game. Typically on one of these games, you want to have the person playing the game lose some money, but you want to have it losing just a little bit. Otherwise, you can't attract people to play. So this seems like actually a pretty decent circus game. If you ever see it, don't play it.